Thanks. I'd like to thank the Secretary for allowing me to give my first presentation at the qNMR workshop. So at first, I present the title is improving the accuracy of qNMR through CCQM comparisons. Okay. So first of all, general quantification of organic compound in analytical chemistry shown here. Normally, pure material evaluated at first and prepare the standard solutions, and quantitative analysis is performed on these standards. So with this scheme, traceable evaluation will need time and cost. In this situation, qNMR contribute to rapid supply of standards. So this is a principle of quantification by qNMR. Formula 1 shows a signal ratio shows a ratio of number of nuclei and concentration ratio. And in case of purity determination, we usually use Formula 2. We need just a ratio of mass and some kind of purity of reference material. So this is the general procedure of qNMR. This shows in case of internal standard method. At first, we weighing mass of analyte and the reference material of proton, and just dissolved by deuterium solvent and prepared solution just measured. For accurate qNMR, we usually evaluate the accuracy of sample preparation and animal measurement and data processing. The combination of all factors provides an accurate result. So we discussed in these factors through the CCQM comparisons. So in OAWG, this is pilot study of qNMR is coordinated two comparisons with different objects. First, pilot study for data acquisition and process in qNMR method as a CCQM pilot study P150. This shows started 2012. Maria shows 2024. Actually, 2024 at 2014 is started the comparison, but we suggest proposed in these years. In this part of study, the participant is 18 countries and 20 laboratories. This shows qNMR is very interested in between the NMIs. And second, CCQM comparison is advanced pilot study for data acquisition and process in qNMR. This as a CCQM pilot P150B. This is the first, almost all same participant. So this is a discussion in these comparisons, including sample preparation and animal measurement, data processing, and including another factor is a condition of instrument and signal shape and width for signal to noise. We discussed many kinds of factors for accurate qNMR. This is a protocol for pilot study P150. The material is here. Internal standard is 3,5-bis trifluoromethyl benzoic acid. This is provided by as a NMR CRM now, and study material as an analyte is dimethyl sulfone, and solvent is methanol, and sample preparation for internal standard method, and we limited the minimum sample size for the site of homogeneity. And in case at the measurement, certain carbon decoupling is off, and another parameters were optimized by each laboratories. So this is an example of NMR spectrum of in this first CCQM comparisons. This shows the internal standard. There is detected two signals, and analyte signal is just a singlet, but next to the methanol signals. So this is a result of CCQM pilot P150. So the following, this is a very good agreement with every participant, with most result in the 0.5 ranges. So it's good agreement. But we discussed the influence of sample preparation. The following, we discussed the classified by resolution of balance used for sample preparation. Overall, participants using high resolution balance shows stable result. High resolution shows this dark blue one. These are very accurate result. And on the other hand, we think this seems to be the little more variation when we use low resolution balance. Low resolution balance shows a red point. This is a small, large variations. So this slide presents the difference of accuracy between the resolution of the balance and the tear combination after pilot study. So the tendency for sample preparation shows to be influenced by the balance used was confirmed. So almost all participants use several kinds of balance, semi-micro balance, micro balance, ultra micro balance. And in case of tear, there is many kinds of tears: aluminum pan or cup, and glass board and bias. So of course, using a high resolution balance, this shows ultra micro balance with aluminum pan. So of course, using high resolution balance and light tear provide higher accuracy. This is a minimum sample size shows accuracy of sample preparation. But we have confirmed that setting and appropriate sample volume using a combination of balance, resolution, and tear is sufficient for accurate sample preparation. For example, in case of using micro balance with aluminum pan, the minimum sample size is near values with most accurate ones. So next, we discuss data processing. Data processing was discussed next sample preparation in OAWG. Since only 1/3, here it is, only 1/3 of the laboratories included the median value for the reference value. We discussed the influence of data processing on the quantitative value. Of course, all laboratory results included the reference value within the, not all, sorry, almost all within the uncertainty range, but with some bias. So we'll discuss the data processing. NMIJ reprocessed all FYDs in these comparisons. Reanalysis of all data by NMIJ to evaluate the influence of data processing for qNMR result. This is an example of data processing competition. Software used by Metrology Nova and phase correction by manuals, and integral range is set to outside of carbon-13 satellite. So the integral range may be influenced to be signal area. So we set the completely same conditions. And baseline correction is set to segment. Segment means linear. So in this approach, window function was not used for all FIDs because in case of using window functions, raw NMR data is sometimes changed. This is a result of the reprocessed result. So as you showed, half of the laboratory is included the reference values. So in this case, the reprocessed result in the integral range compared with the reported result. Some result is not so changed. So next, we discussed the influence of signal shape and width. So it is difficult to discuss in detail, but we evaluate the influence of signal shape for the result. Signal shape is influenced by the condition of magnet. Left side is based on FWHM. FWHM is shows the full width at half maximum, which is the width of the signal at half the height of the signal. So right side is based on the width at the height of carbon satellite. Both tendency is almost all same. And at the case of large width, the variation and bias deviation is more larger. And of course, in case of more sharp result, is good repeatability. So shimming is one of the most important factor for accurate quantification. Shimming is a conditioning of magnet. So this is obtained knowledge by pilot study P550. Sample in case of sample preparation, balance and sampling mass is more influenced in this case. So next, NMR measurement. Today, I'm not show the in detail. NMR measurement is an influence of measurement parameter for could not be confirmed because sample preparation and data processing were more influenced in this comparison. And that in case of data processing, all the setup of the integral range was an important factor for obtaining accurate signal area, and includes including contributions of influence difference with signal to noise of a signal. And also, we summarize shimming was influenced greatly for quantitative result. So next, we coordinated another advanced comparison for qNMR. Advanced means a more actual sample, or using actual sample. Criteria for selecting of the candidate analysis here. One is 2 or more candidated target proton signal exist. So, and easy to handle because if some kind of another factor, it is difficult to discuss the accuracy. So, and enough amount of sample is obtainable. So, we selected this pesticide pre-which curve. We used this sample for advanced comparisons. Here is NMR spectrum for pre-which curve at acetonitrile. There is alkyl proton shows tertiary butyl, and another alkyl proton is next to, sorry, this is not here, O-methyl and N-methyl. And aromatic proton shows benzoic ring and pyridine rings. So in this comparison, we discuss the first signal selection because the protocol is almost all free. So there are many kind of results. So we need to discuss many kind of factors. Here is a signal selection. Blue line is a reported value. And red line is evaluated but and omitted in the report. So at first, I show the pure signal in this comparison samples here inside of aromatic area. So this is the initial result of advanced comparison. There is we categorize 4 categories. A is selecting pure signal. A is not so many, just LGC. And B is subtracting impurity content after determination. And C also subtracting impurity signals on spectrum. And D is no impurity subtraction. As you know, ABC result is good agreement between several laboratories and classified by D is also agreement within same approach. In this result, in this comparison, the sample is included impurity. So we discuss signal selection. And green line is read data processing. Read data processing is based on the resolution of magnet. The result is changed here. Classified A and C is all participants is good agreement with all participants. So this is a contribution of uncertainty component. So actually there are many differences between the NMIs. One of the some kind of laboratories show main component is measurement, repeatability. Some laboratory is including weighing. So this is a last result of comparison. Difference value is determined by mass balance approach. Almost all laboratories good argument with between the mass balance approach. And we evaluated another analysis. Weighing mean is a small reference value. So obtained accurate acknowledgement by this comparison, the signal selection is important. And at the time, uncertainty estimation is difficult is result. Also, the effect of uncertainty factor in qNMR is changed by the CRM and balance used. The accurate quantitative result can be obtained by correct uncertainty estimation. Summary is here, and discuss the optimization of the sample preparation and NMR measurement and data analysis factor based on comparative result of qNMR lead to accuracy. So this is just a commercial image sharing for qNMR is provided here. Two kinds of material for proton and fluorine. One is a proton. So this is a new one, 24-cic acid for proton and phosphorus. And this is provided coming soon. Thank you for your attention. Thank you.
Thank you, Taichi. Very nice presentation with an overview of the history. I think I can certainly say this for myself. Those pilot studies were an amazing learning experience for us, and they really helped us shape our procedures and the way we do qNMR to obtain high accuracy traceable results. So do we have? Yeah, we have 5 minutes, so we have time for questions. Any questions online or in the room here? Look at the chat here. So if you're online, you can do what you prefer. You can raise your hand. You can just turn on your camera and start speaking, or type in the chat. We'll try to monitor as diligently as possible. And if you're on site, just raise your hand.
Yeah, there's one in the chat there.
Okay, so do you want to speak, Benny, or should I just read it? Okay. So Benny Tong is asking Taichi if the NMR software, if you've observed in your study, whether the NMR software plays any difference in the results.
Okay. At first, in case of the lead data processing, at last I used MNOVA, but or just one data. We check the difference of software. We used delta by JO and top spin by Bruca and Metrology. There is no difference by software, but the trend is sometimes it's different. So if you would like to obtain the accurate result, at first you evaluate the accuracy of software by using two kinds of CRMs. It's important for validation.
Good. Thank you,
Thanks,
Taichi.
Yeah.
Do we have any other questions for Taichi?
Yeah, I do. Taichi, I would like to know, because it was NMIJ that coordinated these really valuable studies at the time. But when completing them, were there other parameters that you felt, would have been the next steps that we should have looked at if we were to continue straight afterwards?
Next step is difficult, but I would like to discuss for alternative nuclei, including fluorine or phosphorus, it is very interesting. We also provide some kind of alternative nucleized CRMs. So we would like to discuss another nuclease. Next step, I hope.
Hello, good morning. I'm Wagner from Meyer in Brazil. And I will talk today about the qNMR using other nuclei. I'll talk about fluorine and also about carbon-13.
Maybe click one time in the presentation. I think it was the last time helping.
Yeah, the same thing happened before. So fluorine is a good nucleus for qNMR because we have like near 20% of the pharmaceuticals containing fluorine. And also we have fluorine in other compounds like agrochemicals and PFAS and many others. It has a very large range of chemical shift, so we have less risk of overlapping peaks compared to proton NMR. And also its sensitivity is very high, almost the same as the one you find for proton. So this large range of chemical shift at the same time is good to avoid overlapping peaks, but it's a challenge because we should ensure that the response is linear or across different regions of the spectrum. So the fluorine spectrum has near 700 ppm. If we focus on organic compounds, then we will find like 200 ppm. So here we have an example of a CF3 group whose chemical shift is minus 64 ppm. And we could have this as an internal standard and also a sample with aromatic fluorine around minus 108 ppm. So almost 50 ppm distance one from the other. And this is the excitation profile of an ordinary 90 degrees square pulse. So here I'm showing only 80 ppm. And even in this range, we can find when we are like 40 ppm distant from the transmitter offset, we can have a loss of the signal of over 5%. So it can make a big difference in qNMR. This non-uniform excitation profile may come from mostly two different reasons. One is the lack of linearity of the receiver. And to improve this, we don't have much to do in the software. We should have like an instrument upgrade, like a console upgrade. And the other reason is the limitation to deliver broadband pulses. And here we can do something to improve the irradiation profile. For example, we can change the experimental parameters in one side using like square pulses. We can use smaller pulse lengths because the more narrow is the pulse length, the wider is the excitation profile. So we could, to do this, we could increase the pulse power of the pulse power level. But here it depends on the probe because we cannot increase too much, otherwise we can cause damage to the probe. But also we can use smaller flip angles. Usually for proton, we use 90 degrees pulse for qNMR. We could try smaller ones. Another option is to use shaped pulses like those using adiabatic pulses. There is a paper from 2016 talking about this chorus pulse. It was aimed to solve these fluorine problems. Another option would be like a probe upgrade, because depending on the probe, you can have higher pulse levels, so then you can use like smaller pulse widths, but then you need to change your instrument. So this work I did here at the BIPM in 2023 during my secondment here. So these results are from a GEOL instrument at 400 megahertz per proton. So here I tried the excitation profile over 700 ppm. For 90 degrees pulse, I got this, and then I reduced the flip angle. It improved. I mean, I got a little bit more flat excitation profile. But when we look at 80 ppm, focusing on this region, which is a distance that we usually will find for organic analysis, then the difference is very small. We can see that the 90 degrees is a little bit more pure than the others, but no big difference. So I tried to compare the signal loss we had to one side and to the other side, aiming at compensating these signal losses from the analyte and internal standard. Maybe if we lose the same amount of signal in the two peaks, these losses would be compensated. So here I am the same results, but here I'm comparing the signal losses depending on the offset to one side and to the other side of the transmitter frequency. So the blue is the negative side and the gray is the positive one. And I did these plots here to make it easier, the comparison of these losses. So if we had the same loss to one side and the other side, we should, if we put the two signals together, we should have 50-50. This would be the ideal situation to compensate these losses. So here for the 90 degrees pulses, we had this in most of the experiments. And for the smaller pulse angles, then the results were worse. So the best conditions here was with the 90 degrees pulse. Decreasing the pulse length didn't improve the result. Then we tried other two things. One was an increase in the pulse power, respecting the safe limit of the probe. In this system, we set the attenuation, so a smaller attenuation means a higher pulse power. And also we tried the use of digital filtering. So these two plots here, they are using digital filtering. The dashed lines is with smaller attenuation and higher pulse power. So we see that using a smaller attenuation makes a small difference. And the use of digital filter makes the profile more flat at the cost of introducing some waves, it's like a wave pattern here. So this can make the response less symmetrical, and at the end you have a bad result, or a worse result. So still the 90 degrees pulse without the use of digital filtering was the best situation, and increasing the pulse power made almost no difference. So there's no reason to work close to the limit of the probe, because we didn't have a good improvement. So using like square pulses for fluorine, some key points, the 90 degrees was better than the other pulse angles. We should place the offset exactly midway between the peak and the internal standard to compensate the signal losses with no digital filtering. And the distance between the analyte and the internal standard should not exceed 26 kilohertz. In this equipment we were using, that was a 400 megahertz for hydrogen. This means 70 ppm, because over 70 we start to like 35 ppm for each side. Beyond this we start to have more more difference here. The other option was to use shaped pulses. This is the paper that developed this sequence named Chorus. It's from 2016 from the University of Manchester. And they compared this sequence with a square 90 degrees pulse. So they got much flatter excitation profile using this Chorus sequence compared to the square pulse. So we did this here, and we got this one in the middle. It was much better than the square pulse, but at the same time was not the same as we found in the paper. Then we talked to the technicians from Yao, and they suggested using these shifted laminar pulses. So in this case, we have excitation in different regions of the spectrum. So to do this experiment, I put the receiver frequency on resonance, I mean the resonance of the molecule, the signal that I was measuring, and did the offset variation in the laminar frequency. And then we got the result very similar to the one they had published. So this was over 700 BPM. So we got this very uniform and appears in a 80 ppm range, also good results. So using this Chorus sequence, we got very uniform excitation profile over 226 kilohertz, which was 600 ppm in our instrument. It's a promising alternative, particularly when you have to integrate more than 2 peaks. It may have some problems if you are working with polyfluorinated samples like PFAS, for example, because the duration of these pulses is long. It's like 6 milliseconds, and then a square 90 degrees pulse would be around 10 to 15 microseconds. So it's a big difference. You can start to have some homonuclear coupling here in a polyfluorinated compound. And now let's talk a little bit about the integration of the fluorine signals. We have here in the left, we have the hydrogen spectrum of this BPFMBA. As Annie just showed us, it has some peaks around 8, the aromatic proton around 8 ppm. If we look at the carbon-13 satellites, for example, this one and these, they are the satellites of this main peak, and they are very symmetric around the main peak. When we look at the fluorine spectrum, then in this case, this molecule is very symmetric. So we have 6 fluorine nuclei, but only 1 chemical shift for all of them. So here's the main peak when the fluorine not bonded to a carbon-13. When the fluorine is bonded directly to a carbon-13, then we will have this pair of satellites. And as you can see, they are not symmetric around the main peak because we have an isotope effect. The fluorine bonded to a carbon-13 has a different chemical shift from the fluorine bonded to a carbon-12. And we can fill this up to 2 bonds of distance. So for example, here the fluorine has a carbon-13 in the second bond, and still we have a symmetric satellite. This means that if we use the same procedures we normally use for proton NMR, we may have some bias. So here, if we use this option of, this is the same spectrum of this molecule with a big zoom close to the peak base. So if we use 30 Hertz beyond the furthest satellites, it seems okay to the upfield or to the right side, but to the left, we still have some peak area. I mean, the peak line didn't reach the baseline yet, and we would stop the integration here. We'll miss some signal. If we use 76 times the with at half maximum, then we would miss one of the satellites. So we tried different lengths beyond the different numbers of ppm of hertz, sorry, beyond the satellites. And to the upfield, to the right side, we found that 30 hertz, as we use for proton, is okay. But to the left side, we got better results using 120 hertz after the satellite, more precise results. So using these parameters, we did a quantification of this difluorobenzophenone using BTFMBA as the internal standard. Here are the results using proton NMR, and the results using fluorine were good, were like inside the uncertainty range. So we could use the square 90-degree response or the close sequence, and we got good results with both of them. This was the certified guide. So we put all these recommendations in this internal standard reference data from the BIPM. This work had been started here by Klas, and then we had Leandro from Argentina, then me, Taichi collaborated in the revision of the document, and also Gustavo and Steven here from the BIPM. Thank you, guys. So you can find this in this link here. Now let's talk about carbon. Carbon is a nucleus that we will find in all the organic molecules. Its chemical shape also span a range of a wide range of close to 200 ppm. So we also have smaller risk of overlapping peaks, so like the same as fluorine. For this reason, it requires a uniform excitation profile over a wide range. The sensitivity here is very small. It's almost 6,000 times less sensitive than proton. It has slow relaxation times, so this demands the use of long experiments and also to include the relaxation agents. Otherwise, it gets not feasible to do in a reasonable time. And it has strong heteronuclear coupling with hydrogen. So we have to decouple hydrogen to avoid signal overlapping, because the splitting pattern of carbon would be so wide and they could overlap. And when we do decoupling, we can have the nuclear Overhauser effect. I mean, part of the radiation used to decouple the hydrogen will be transferred into the carbon-13 and will increase its signal, and not in a quantitative way. So we should avoid the NOE here. So the best thing to do this is to use this inverse gate decoupling. So we will do the decoupling only during the signal acquisition and not before, as this showcase here. And another thing, we can use the most common sequence used for hydrogen decoupling when we are observing carbon-13 is the VALT16, or there are other sequences based on the same composed pulse that we have in VALT. But also we can have adiabatic pulses to decouple the hydrogen here. And there is a number of papers published by this group from Professor Acoca initially, from the University of Nantes here in France, doing this adiabatic decoupling. They work with site-specific isotope ratio determinations, and the determination of the isotope ratio in each position of a molecule. And so they have shown that this adiabatic decoupling was better. This is a figure of one of their papers, this one. So here they did experiments using acetic acid and ethanol, both B-labeled, I mean, with only carbon-13. So if they didn't have any bad influence of the decoupling of hydrogen, they should have the same integral for the 2 carbons in each molecule. This experiment in the left was with valve 16. So here they found difference between the 2 signals of over 30 per mil, or 3%. When they used adiabatic decoupling, this difference were below 2 per mil. So it was a big difference. So this shows that the adiabatic decoupling is better to not to include bias in the qNMR. So we did a comparison using, in one case, hard 90 degrees pulses, using either valves or adiabatic decoupling. And then we used the chorus, the same one that I showed before for fluorine, using either valves or adiabatic decoupling. This chorus we published because we didn't find in the literature the combination of these chorus pools for carbon and also the adiabatic decoupling for hydrogen. And the sequence for adiabatic decoupling was published by this group of Professor Acoca in 2007, the chorus in 2016, and in 2018 we did this. This was done during my PhD studies, and Bruno was one of my advisors, so we did this together. This experiment shows the result we had for, usually the carbon-13 isotope ratio is measured in terms of a unit called delta carbon-13. And so we measured this delta of carbon-13 in each position of the molecule. And we did delta-delta, which is the difference between the delta of each position and the delta of the whole molecule. That's why it's delta-delta. And we did the decoupling varying the offset of the decoupling. So this molecule, we use toluene here. It has one proton signal around 2.3 and the aromatic around 7.2 or 7.3. So we tried these 2 sequences and these 2 frequencies and also one in the middle. If the decoupling was efficient in the whole hydrogen spectrum, we should have the same result no matter of the frequency of decoupling. And we almost saw this when we, in experiments B and D, both using adiabatic decoupling. When we used valve 16, we found some difference depending on the position, no matter if we had used a hard pulse or chorus to excite the carbon. So we also showed here that this adiabatic decoupling is very better for this qNMR experiment. Here we did the same toluene molecule, a big zoom to show the residual coupling. This spectrum here in red is without the coupling, so we can see the splitting that results from the coupling of carbon to hydrogen. So if we look at this peak around 125 ppm, which is the para position, we have one hydrogen here, so we have like a doublet here. And when we do the coupling, sometimes we see residual peaks from the coupling that was not perfect. So we could see these in like 3 experiments. And when we use this chorus sequence of chorus plus adiabatic decoupling, we couldn't see the residual peaks of the coupling with carbon and hydrogen anymore. Now about the integration. For different when we are doing proton NMR, every proton will be bonded to one carbon in all the cases. Usually we won't use a proton bonded to a nitrogen, for example, for qNMR. For carbon, we can have a carbon that is not bonded to any other carbon. We can have a carbon bond to 1. We can have a carbon bond to 3 or to 2 or even 4. So for each carbon bonded to the one that we are analyzing, we will miss 1.1% of area that will appear as carbon satellites. This results from the carbon-carbon coupling. So in most cases, we cannot have enough sensitivity to integrate and include the satellites in the integration. So the best thing here is to apply a correction factor to the integrals to compensate for the losses that we are having due to this carbon-carbon coupling. So we will multiply each integral value by 1 plus the number of carbons bonded to the observed one times 0.011, which is the isotope abundance of carbon-13. Another thing that we should take into consideration, and we didn't find this in literature before, is the isotope ratio of the whole molecule of the analyte and the internal standard. So here, when we look at the delta carbon-13 for organic molecules, we can have variations. These delta values are with reference formula. I'll come to that. So we can have difference from like -10 to -60 per mil. Sorry, there's a mistake here. The unit is per mil and not percent. So this means almost 50 per mil difference or 5%. So we should consider this isotope ratio of the internal standard and the sample in the results. And as long as possible, we should integrate all the peaks of the carbon because we have like difference, site-specific difference. And if we not consider all the peaks, we'll have some bias. So we did this calculation for this molecule, dimethylphthalate. When we considered like only one peak, we could have over 10% of bias. When we used all peaks, the bias was smaller than 3% or smaller than 2% when we used adiabatic decoupling. So we put this in the calculation. So the ratio of the carbon-13 abundance of the internal standard to the sample. In this case, it was like, this was 0.99, which means a 1% difference that would increase the bias in 1%. And this, the isotope ratio determination by mass spectrometry was the biggest source of uncertainty in our calculations. So we have published this paper here. So to wrap up things, for fluorine, we should post the transmitter frequency exactly midway between the peak and the analyte, especially when we are using 90 degrees post. We should keep the distance between the analyte and the internal standard below 26 kilohertz when using square 90 degrees pulses, or else use broadband sequences. And be careful with the integration because of these asymmetric satellites. For carbon, we recommend using inverse-gated proton decoupling with adiabatic pulses. Try to integrate all carbon peaks to avoid bias from this site-specific isotope distribution. Correct integrals for missing carbon-carbon satellites. And also take into account the carbon-13 abundance of the analyte and the internal standard. Thank you. Yeah.
Thank you, Wagner. So we are right on time.
2 minutes after.
So we'll now have our coffee break before food is over, and we'll come back at I think 11:40. Yeah, is that what we have? Okay. That's-
A lot of things.
Okay, so we're back. I just wanted to confirm with people online, can you hear me?
Yes, we can.
Okay, good, thank you. So, continuing with our second session, the next speaker is myself. So I don't think we need any other introductions here. And I'm gonna talk a little bit about some strategies that we use for achieving high accuracy qNMR measurements in calibration solutions. So I would just like to begin by setting the scene. And actually, we've been discussing high accuracy qNMR in general. And I just wanted to kind of circle back to what the question was when we first started doing the NMIJ studies back in 2012. And the main question we had was if it was possible to achieve 0.1% measurement uncertainty on qNMR. And well, we've been very successful with that. I'm not gonna, that's not the intention of this talk, but just to remind you that if we look at the K55 Aldrin purity study, we have a 0.6 relative standard deviation between 12 participants. And by 2018, with the bisphenol A purity, we have a 0.1% uncertainty, not uncertainty, sorry, relative standard deviation between participants. So we could say that we got a lot better over these years. And as I said earlier, I think that's we owe a great part of that to the studies themselves, because I know we all learned a lot of with those studies. So what I actually wanted to discuss is, okay, we got really better and we got really close to what we wanted to, the 0.1% measurement uncertainty by doing internal standard qNMR in purity or high purity samples. So maybe it's time to move on to more complex measurements. And that's what I kind of wanted to try to bring up here today. And it's time, I think it's time for us to move on to more complex measurements and more complex samples, not only because we want to, but because actually many of us NMIs are doing it in our daily lives and in the services we provide. So as the CCQM, we should really be trying to underpin those services. So to tell you a little bit about the history of this in my institute at the NRC, we started this talking about calibration solutions very, very long ago with Holt, where he proposed something called the principle of reciprocity in signal strength calculations. And this is really the 90s, the 80s, maybe even, I don't have the actual date here, I should have, but this is a very, very old principle based on which in 2005, our institute came up with this quantitative 1H NMR for using external standards, which is what then was later called POCON or ERADIC 2 for Bruker users. So it's basically using the principle of reciprocity to correct for pro-Q damping, and then actually defining that the pulse length times intensity is proportional to concentration regardless of solution composition, which enables the use of external standards with this P90 correction. So, as I said, soon after, in 2006, which received a name, POCON, post-length-based concentration determination. It is called ERETIC 2 in some vendor software implementations. You all know who I'm talking about. No direct relation with ERETIC. It's important to highlight ERETIC is the use of electronic references. So in my opinion, this name should be avoided at all costs because it's really misleading. But the whole principle of POCON is actually just using an external standard, but then correcting for post-lengths. It's pretty simple to do mathematically, but it's pretty effective. And as I said, we've been doing this for exactly 20 years now, right? Since 2005, and we've been doing it successfully. So if we look at how POCON works on a real sample, we've done this comparison in mate extracts, just for a simple validation of this study, of this method. We've extracted mate and then analyzed caffeine by GCMS and NMR in the exact same extract. So it was actually all done in deuterated solvent, and then we analyzed it by GCMS and by NMR. So GCMS using standard addition because we wanted to actually be able to measure in the exact same sample without any question whether this measurement was valid or not. So we did it and compared to NMR, and we find very good results, pretty good results, especially considering that this is a vegetable extract with relatively small concentration here. So we validated this method and successfully applied it to a range of real samples in the production of cannabis reference materials. This was work done in Metro, but equally we have this validation study from, as I said, since 2005 at the NRC doing this historically. And why do we actually want to use external calibration? Because you might think, well, yeah, it's good, but why would I use it if I can use internal standard? Well, there is a number of different reasons why we might not want to add internal standards to our samples. In our work at the NRC, one of the reasons, and the main reason probably why we don't want to add internal standards to our samples, is that we work with very, very complex biotoxins for which we have to go through very, very complex isolation processes, and we end up having micrograms when we are lucky enough, few milligrams of material, and that's all you have of that toxin in the world sometimes. So we don't want to put any internal standards in this sample because it would ruin the whole world supply of those toxins. So and for the same reason, sometimes we also want to avoid adding deuterated solvents because we observe that deuterated solvents sometimes they, as we know, there is HD exchanges in some samples, and with some of the toxins, actually these HD exchanges are very easy to happen, but very hard to revert. So we end up having deuterated standards where we wanted to have native standards, and that is not good. So not adding deuterated solvents is also highly desirable in some sample preparation procedures, simply because we might want to avoid some operations, right? If you're analyzing urine, there is no point in trying to remove all of the water from your urine and then reconstituting that in D2O, because that would simply add so much uncertainty to what you're doing that you actually might prefer to analyze water directly. So those are two things I want to talk about, actually, external calibration and how we deal with natural abundance solvents. So dealing with natural abundance solvents is pretty straightforward. Someone would say, from a metabolomics perspective, it is a very popular approach to use the first increment of a nosy sequence using pre-saturation. This is the most popular method throughout the literature. You'll see it in pretty much every metabolomics protocol and pretty much every metabolomics publication. And the way it works, if we look at a water signal here, this is a real sample, a real natural abundance water sample. We will, oh yeah, there it is. We will produce selective pre-saturation of the water signal here to try to reduce that signal as much as possible. But then we have a problem that is called the issue of faraway water. And I know it sounds like a made-up term, and it is a made-up term. Well, in reality, all terms are made up, right? But this one was recently made up by people working on solvent suppression. And what this faraway water means is actually that if you look at your NMR tube, you have a region where nuclei experience pretty much the same effective field when you have a pulse, but then on the boundaries you start to actually have nuclei that are not experiencing the same pulse, and therefore they are not effectively suppressed. Even if you do a very long pre-saturation, you can't get rid of that signal. So that faraway water is a problem when you're doing solvent suppression. And the way the nosy sequence tries to solve it is actually doing something that we call volume selection. And it does it by phase cycling those three pulses that you see, those 3 90-degree pulses, in a very smart way. If you do phase cycling for them, you end up having in between pulses 2 and 3, all your magnetization is in the z-axis, and then you can just use pulse number 3 to actually get the signal you want on the transverse plane, and then when you do that by using those 3 pulses and these phase cycling process instead of simply using a single pulse, this here is the volume selection effect that you get. So the red plot here is what you get with a single 90-degree pulse, and the blue would be just added 90-degree pulses. But when you do these phase cycling, you actually have a much narrower volume of your tube that actually gets excited. So you have this effect of volume selection here. So when you do all of this, you actually get reasonable solvent suppression, and this is what one spectrum looks like when you do nosy solvent suppression. This is still the water signal here, but we can kind of see, and these are all just to these are all actual spectra of a toxin sample, right? So you can't really see anything but water here, and then you start to see other peaks here, and then when you do the full suppression, you can see your analyte peaks, but the water signal is still the most intense signal in your spectrum. And why is that a problem? Well, that's a problem simply because you might be, and as I said, this talk is supposed to be like a provocative talk, and us trying to do more complex qNMR measurements. And if you're doing more complex qNMR measurements, at some point, you're going to start wanting to deal with lower concentrations. And if you want to deal with lower concentrations, your solvent signal being the most intense signal in your spectrum starts to be a problem because it limits your dynamic range, right? And then there's another problem with suppression using nosy, which is actually related to the trueness of the measurements here. you really have, if you're doing solvent suppression using the nosy sequence, you really have to optimize this suppression on a sample by sample basis, which is obviously not what is done in all of those studies in the literature that I just mentioned. So people just follow one protocol and assume everything's fine. But actually, if you use different pulse RF fields, for example, you can see that you can get severely biased results for some analytes, depending on how close or how far they are from the suppressed signal. So it all gets really complicated. And an alternative would be to use suppression via excitation sculpting, which works on a completely different way. So if we use excitation sculpting, the first thing is we don't need to use presaturation, which is already a good thing by itself, because presaturation can also produce saturation transfer, polarization transfer, which leads to distorted signal intensity. So you don't want that in your quantitation. So eliminating, getting rid of the presaturation is already a good thing in itself. And then the way excitation sculpting works is you have a gradient pulse. So it's actually two gradient echoes here. You have a gradient pulse that encodes all your spins. You have one selective 180 rotation here that produces 180 degrees rotation in all your spins except for the solvent. And then you reverse the encoding with the second gradient, and then you just rinse and repeat using gradients of different magnitude. And this is a very important characteristic of the excitation sculpting, is that those two gradient blocks, they have to be independent. So using, then the question is what type of pulse you're actually going to use for that 180 degrees rotation, which leads at the end to different versions of the sequence. So the so-called Shaka sequence actually uses a selective 180 and then another broadband 180, so that you are rotating the solvent selectively by 180 degrees, and then you rotate everything by 180 degrees. So the result of this block is 0 rotation for the solvent and 180 rotation for all the rest. And this works really well for qualitative analysis. So if you look at a sample with where you have chloroform, for example, and this is not CDCl3, okay? This is my mistake. This is, of course, natural abundance chloroform. So if you have chloroform here, and you suppress using that sequence, you have a very, very, very good suppression and very selective. So you can see that actually these are the chloroform carbon-13 satellites, and while the main signal is completely gone. So, and it's very selective because you can actually suppress that signal without even affecting the satellites. So it's beautiful, but it has a problem. Well, it has, one thing is we have to define how far from the suppressed signal we have to be to actually get good results. So obviously we can fine tune that if we make that shaped pulse more selective, and to make that shaped pulse more selective, we just have to make it longer. So when we have a very, very long pulse, we have very, very accurate results, which looks really great, but then you have a 40 millisecond pulse, which obviously leads to T2 losses and then biased results because you're losing magnetization via relaxation. So that's the problem with the excitation sculpting using the Shaka sequence. So then again, we need another alternative, and then we turn to binomial-like sequences. And binomial-like sequences are sequences that use trains of pulses, and the most commonly known of those are the 3919 and the W5 pulses. And the problem historically with those binomial-like sequences is that because they're also longer than, of course, simple pulse acquired sequences, they start to if you have strong couplings in your samples, you start to see J modulation artifacts, and then they lead to phasing issues like this, and of course also to signal losses. But there are alternatives to avoid this issue, and the main alternative was published also by the Manchester group in 2012, 2013. They implemented the binomial-like sequences with a perfect echo, and they've completely solved this issue. So what we did recently was we actually came up with several combinations of binomial-like pulses and also some more recent interesting pulses that are called the WADE pulses, WADE for water irradiation devoid pulses. So these are artificial intelligence designed pulses that produce excitation of the whole spectrum except the solvent. And we combined all of those several binomial-like pulses and also the WADE pulses with the perfect echo from Manchester. And we get this simply amazing suppression here that we can see compared to NOESY. So this is the same spectrum that you saw earlier for NOESY. It looked good at that time, but now compared to the Robust 5 sequence, you can see that the suppression produced by the Robust 5 sequence is much better, and you can't even tell that this was done in natural abundance solvent. And when you compare here different types of sequences that we used in this work, you can also see that not only the Robust 5, but also the weight-based and the JRS, which is another type of binomial-like sequence. They're also producing very good suppression results. Then, well, why is that useful? So, few practical examples. The first one is for a new cyanotoxin we're working on. As I said, we have 800 micrograms, which is pretty much the world supply of that toxin. So we are doing all of this in a 700 megahertz magnet with a cryoprobe. And then if you acquire this using your simple pulse acquired sequence, that's what you get. All you can see here is lots of water, lots of radiation damping, and nothing very useful in this spectrum here. But then if you use the binomial-like sequence, that's what you get in exactly same tube here. So you can see a full perfect spectrum for those 800 micrograms of toxin. And the other thing we did was we implemented those suppression methods in an inversion recovery sequence to actually be able to measure T1 and do proper high accuracy quantitation here. So as you can see from the inversion recovery curves here, we have very good T1 exponential profiles, even though, again, we are working with 800 micrograms of a toxin in natural abundance solvent. So that's very good, and we can very accurately determine those T1s. And also, we had to consider both relaxation losses during the sequence, because, again, this sequence is not a simple pulse-acquired sequence. And although we've tried to keep those pulses as short as possible, they're not negligible. They're something in the range of 10 microseconds total since for the whole sequence. So you still have potentially some relaxation losses that you have to compensate depending on depending on how large your T1s are. If they are very short, then you can actually have some impact, and we are correcting for that because we can actually measure T1 and T2, and we can correct for potential relaxation losses here. And then the other thing we are also correcting for and accounting for in our uncertainty budget is the excitation profile, which is of course not as perfectly flat as you would have for a single pulse. The moment you start adding pulses to your sequence, you start getting excitation profiles that are not perfectly flat, and that's just life. That's just how things are. But we can always correct for that as long as we have a very good knowledge of how those excitation profiles are. So those are two things we have to consider in our uncertainty budgets here. And at the end, we can actually measure that those 800 micrograms of toxin using, again, external calibration and these suppression sequences, those are actually 671 micrograms of toxin with an uncertainty of about 1.5%, which is pretty good for, and it's perfectly fit for purpose for what we are doing. And then again, this was determined in the solution where the toxin was isolated, so we don't have to, deal with changing the toxin from one solvent to another, risking degrading what we have of the toxin. So this is a very good outcome for this suppression sequence. But then what if we have even worse cases where we have something like 100 micrograms of a toxin in water, and now because we are isolating this using semi-prep or prep HPLC, we can also have mobile phase additives here, such as formic acid. So this is what we got for another toxin where we have 1% formic acid here. So instead of just seeing one signal, one water signal, you are seeing one water and one formic acid signal. And to make things easier in this case, we only had 70 microliters of this solution, which actually, to be honest, made it easier, because then instead of adding more water, we just added D2O. So we would have less water to actually suppress. So this is what this thing looks like with suppression. Then again, you can see the carbon-13 satellites here, and they are not perfectly symmetric because this sequence is not as selective as the other one, because we are trying to keep the pulses short. But then again, we just have to make sure that we are not quantitating anything within that region where we still have some residual suppression, and we know exactly the width of that region. So that's not a problem, and we can just calculate and we get, again, 103 micrograms of toxin with a 1.7% uncertainty roughly, which is pretty good. And then what we do in our CRM production is actually we just dilute that sample ample, and that's our CRM. So that's, again, as I said, that's why we don't want to add anything to those toxins, because that would make things really hard for us to actually deal with it. So just to wrap up, external calibration and novel solvent suppression schemes are extremely useful tools that allow us to measure samples beyond the traditional high accuracy qNMR applications. Of course, we have to consider what is fit for purpose here. We are not looking to doing this with a 0.1% uncertainty, but we can get pretty nice fit for purpose uncertainties with this. The sequences that we developed enable high accuracy measurements at very low concentrations and accurate T1 determinations. T2 determinations are being added to this to come. Resultant uncertainty budgets should consider, as I said, additional allowances, because we know we have some additional uncertainties playing a role in here. And then my proposal again is that qNMR in this type of samples should be explored in future comparisons or pilot studies. And it doesn't have to be 800 micrograms of sample in natural abundance solvents, but maybe calibration solutions would be a nice way of starting to deal with something that is a bit more complex than just pure samples. So my special thanks for Kelly, Sabrina, Dan, and Pierce at our team at the NRC Biotoxin Metrology, Andy Selwood and the Cawthorne Institute in New Zealand, who are actually the ones isolating those toxin samples, and Lucas at Metro for the partnership, and also qNMR data for the suppression sequences, nosy, metabolomics, and all that. So thank you.
Yeah, no, it's working. It's working. No, it's working. Okay, just takes a bit of time. Yeah. So now I want to talk like a little bit about like the deconvolution. So we get in the next session, which is like more advanced data processing, and I will take care on like some applications that we do, which are a little bit less metrological. So I like talk about like benchtop NMR spectroscopy, but it's also a thing that we do at BAM in our more like process monitoring work, bringing these compact instruments really into the field, which is then in this case, the field would be an industrial plant setting, and also like using some more advanced data processing with it. But no worries, we will hear something from LGC on like some uncertainties later on in the next presentation after lunch. So what does it mean when we're talking about deconvolution? So basically it's extracting information from individual signals of the NMR spectrum. So you can see this is like a simulation here. We are starting with two signals which are simulated. This would be looking in the frequency domain, and this would look the same in the time domain. And if you decon both that, which is basically an unfolding process of two individual functions, which comes from the mathematical point of view, you can get some individual signal information here and get basically in the simulation, which is pretty boring, getting back to a table. But typically you don't start with a simulation, but you just deconvolute a real spectrum. And then the aim of it is to extract something like the peak position, intensity width, or like in our case in qNMR, most of the cases the signal area, which we can then use for quantitative results. So why should we do this in the first place? We've seen like in the presentations earlier today, like this is pretty nice. You can do some integration of the signals. You can like of course have to think about integrating the whole signal. You can think about okay integrating it with or without the carbon-13 satellites. So basically, in theory, you have to cover for ideal Lorentzian function like 64 times the line width at half height for 99%, sometimes even larger. So if you go to like a 99.9%, it's even getting very, very large here. And this depends, of course, on the like full width at half maximum. So in case of like some signals that having a quite realistic range, you get a very, very broad range to integrate here, which could be impractical due to like large number of other signals in there, which you can then integrate with it, or even some partial overlap, even on very small integration ranges. So what you can do is you can use that in different cases here. I just took some examples. First would be you have like, for example, some broad lines here in the baseline, which can be from your signal of interest, but also can be in the other case of like, for example, some water signal that's still in there. You can have some structurally related impurities, which would be most of the cases what we are dealing with here. So having a high purity substance, but some very structurally related impurities that are sitting on the edge of the signal that we would need to compensate for in the integration. Or you can have also like an overlap of like two species in the same range of the spectrum. In this case, this is some illicit drug sample here, which is showing a doublet of like NDMA here and like a doublet of doublets of NDE, which you can then also deconvolute by just fitting this with some functions. So we need some other methods to get the most accurate signal area. So this means if you can integrate it, keep it simple, because there's no need for deconvolution methods, because you will always have some kind of loss and some kind of like optimization problem when fitting it with some of these functions. But if you can't do it to get the most accurate result, you need to find out some other ways with some line fitting, and I will come to that in a moment. So we have a quite big toolbox available in commercial software, but also in like do-it-yourself approaches. So I will talk a bit about line fitting, about global spectral deconvolution. This is something that Nova is pretty famous, like promoting it in the software edited sum. You can have some chemometric modeling. I don't want to get into details today. This is something which is pretty well known from other fields, like using partially expressed regression, multivariate curve resolution. You can find some software that are also like capable of doing NMR spectrum, like PeakSect or like Unscrambler, other things. And of course, you can do it yourself in MATLAB, in Python, and or whatever programming language you're looking for, and you are capable of doing some things. And I want to talk briefly about like indirect path modeling, because this is something we are applying a lot on benchtop NMR data in almost like, from the first view, like impossible situations, and also a little bit on machine learning, but also like with a little bit of like limitations that you can apply that. When you do some line fitting, you also need to make sure that you take the right model of the line width, line shape function here. So as mentioned before, typically NMR lines in an ideal case would be a Lorentzian, but typically you also find some Gaussian broadening on it. So most common for like this qNMR applications would be like a mixture of Lorentzian and the Gaussian function. For example, like this GSD in Nova, you find another term like a generalized Lorentzian, and you can see the coverage of the fitting to a real signal would cover only 98% here. So this is it's nice for what it's meant to be used, like extracting peak features for example, automated structure verification, getting some multiple data, and it's also like why they're doing it. It's a very fast technique, so you can save some computational cost here. But if you want to have some accurate signal areas, you don't want to use this. If you can choose between different models, you need to like ask yourself what would be the right choice here for fitting my peaks here. And you can see in one example here, and you get some broad feature in this spectrum. So if you just do some integration, you can see a large influence of these signals very close to this broad feature. And if you do some line fitting, in this case, it's done with the Lorentzian Gaussian mixture, you can see much better results here. You can still see there are some deviations in the second decimal from the ideal value that you would expect in this case. But of course, you need to always have some drawbacks here. So, I mean, we are talking about now getting the most accurate result that we can do in this region if we can't avoid it by, for example, using some other signal region or some other ways to compensate for it. Another thing that you can apply to it, it's a mixture in between like a sum integration and the like deconvolution method here, is by fitting an impurity that's sitting on the edge of the signal, and this is called edited sum and you can find some details in this paper of a fellow colleague, Thorsten Schönberger, who developed this, and they implemented it into Nova software, so you can use it right away into the software there. You can flag this peak, it gets fitted, and then it gets subtracted by using a scaling factor from the overall integral. So you can correct this by these small impurity signals, but of course also this has limitations. They spend a lot of like validation effort in this paper, so I highly recommend if you're interested in it to have a look at this. So what's happening if this gets closer to here, and of course you see some limitations in fitting it, especially if you only see a shoulder in the end. So it must be an option to like just fitting it, but this is very nice, and I used it before in the structurally related impurities, because you can very much like compensate for this impurity signals that are very close, also like inside the carbon-13 satellite range here. Another thing that they call like global spectral deconvolution is basically fitting the whole spectrum. And you can see three different options, like on the same spectrum, three different approaches here. One would be the deconvolution by using a line fitting approach with individual signal regions. One would be the global spectral deconvolution approach, which you can see, this is because of this generalized Lorentzian approach, which is very fast and works basically on a single shot and very short computational power on the full spectrum. You can see some very high residuals here, and this, of course, lead you into some problems when you want to use this for an accurate qNMR result. So then they found out that people are interested in using this also for quantitative results, and they implemented something like qGSD, which is then also using multiple iterations, because for extracting the peak features at all, like you don't need this precision, but if you want to go into like a more quantitative result, you should also like spend a little bit more time and computational effort to optimize the signal, because this is basically just an optimization problem to get some accurate signal areas. And this really improved it. And this is also like the base why this edited sum works quite well, because typically they use the same way in peak picking and like doing this option to correct for this edited sum. So you should be taking care, if you want to use these kind of things, especially like in Nova, to select the right peak picking option, which would be in this case qGSD over like the general GSD option. So now getting to benchtop NMR. So everything what I showed you now before was basically high field. So what's about like benchtop NMR? How we use this? So you can see different setups here. These are the systems. Typically, they are like in like a weight range of like 50 to 160 kilograms, depending on the magnet. You can still move it around. They don't need any cryogens. So this is a permanent magnet. It's basically just needing a wall socket, and you let it equilibrate in temperature for a certain time, and then you can leave it on and like move it around. You can even put it into the fume hood, or put it into, like, you can see this is like a 50-liter gas bottle, so they're pretty insensitive to big magnetic masses in the vicinity here. And this is an option, the thing that we developed together with an industrial partner to even bring this into an industrial environment with like taking care of explosion safety, fully automated runtime, so no one is looking at the spectrum anymore and just reporting basically numbers to the plant's operating staff to control the process. So for this, of course, we need to have like a decent amount of automation that we can trust on, and therefore we using different approaches for these broader signals. Don't get me wrong, like sometimes people talking about low resolution NMR, and I think this was stated a lot in the early times of benchtop NMR, but it's not really a resolution thing. So it's more like a spectral dispersion thing. You can see this is a comparison between a 500 megahertz spectrum of these two reference compounds here in a 200 millimolar range in DMS-OD6. And you can see that these peaks appear much broader, of course, like in these benchtop spectrum. Here in this case, this is a very ideal case because you still have some baseline separation in between these two aromatic signals. But of course, in most of the cases in real world samples, you won't see that. So this was actually something we did in an interlaboratory comparison with some people like testing different benchtop NMR systems and wanted to be able to integrate these signals. But in case of a real process sample, this is what an experimental spectrum of an aromatic signal looks like. And when I first saw that, I wasn't sure if we can get anything from it. So with this option, this was basically a spectrum of a reaction taking place between fluoronitrobenzene, aniline with a organometallic lithium reagent to like this NDPA, which is shown here in blue. And you can see these three components. What we're now doing is a so-called indirect hard modeling. So we are leaving the fitting of individual peaks for individual signals, and we just use pure component models. So we know what we have in this mixture. Luckily, we know it because we know what the reaction is taking place. So we can do the individual spectrum, in this case of this fluoronitrobenzene, of the aniline, and of this product here, and we fit this with these Lorentzian and Gaussian functions here and create some pure component models that we combine to a mixture model. And this mixture model is then fitted in an global optimization problem to the experimental spectrum. And the nice thing in benchtop NMR spectra is due to the lower signal dispersion, you can see some things like called higher order couplings because the J coupling and the chemical shift dispersion comes closer together in comparison to like a high field NMR. So this in the first place looks more complicated from a visual point of view, but gives us here some features in parts of this very overlaid spectrum here that allows the algorithm to find some specific regions to fit these pure component models to the actual mixture model, which then is basically an optimization problem with some degrees of freedom like position, height, and width. And of course, you can see there's a lot of like individual functions. So this can take quite a bit for optimization, especially when it comes to like, we want to apply this in real time. So we are talking about like a couple of seconds, like 10 to 15 seconds of calculating time, even like on a regular computer, which we are using for this kind of applications. So this was on a commercial software under some MATLAB scripts. So I had a visiting scientist recently in my lab, and he was from Chairman in Florence in Italy, and he was like a guy that did some solid state optimization stuff in Python already, having a nice package framework to apply for the chemist, and he wanted to implement this indirect hard modeling approach into this Python thing. So you can see a recent publication of this here with all the details. I don't want to go like too much into detail, but basically it's the same principle that I just showed you. We have like an initial guess for each component. This can be done by experimental spectrum, but also by simulated spectrum. And I will come to that in a moment where you can also use that for a favor. And we select the regions of interest and optimize first the chemical shift, which is more like an alignment, which is also a very interesting optimization problem, because especially if you have very sharp peaks, you can have a lot like local minima that can be very interesting in like aligning these before performing then all the parameters to get component concentrations. And this was done within a package which is called Klas, which is a Python package that you can download for free. It's a free of charge thing you can download from GitHub, and it's implemented in there. It's very versatile when it comes to like raw data compatibility. So you can include all kind of different data sets from manufacturers. You can do some basic but also advanced processing. It comes a bit from like denoising of data and 2D data in solid state, but then it grows and grows and grows. So it's still in development. And it's very, very good documented. So the nice thing is you get a like 150 pages manual there you can download all like these different settings, and also like some graphic user interfaces if you're not so much into coding. So I'm inviting you to like have a look at this if you're interested in, and it's an open source thing, so you can also like get some improvements done, also like get in contact with the coding people there. So we tested this on a simple mixture, trying to compare it with a regular integration approach. So we did that on a mixture of benzoic acid and ethylene carbonate here, and running into like quite similar results here. Of course, there are still some deviations, but this is an unfair, from like the deconvolution point of view, it's quite an unfair comparison, because here you can integrate. So here we have nice and separate signals. So of course we are not expecting, because you will have some residuals from the fit, from like imperfections. We talked about it before, like having some imperfections from shimming, having some imperfections from other influences. So of course, in this case, I would have expected the integration to be like better than the indirect carbon modeling, but we are getting close, very close to it. So when we wanted to publish that, we get of course ask, okay, why you just applied it to a very easy situation? Show me that it's actually possible to run it on a more complex mixture. And we found a sample from a metabolomics approach from Florence, actually, with a mock-urine sample containing 10 metabolites, each on a 10 millimolar concentration using DSS and an internal standard. And we compared it to like some state-of-the-art software, which would be like qNMR in this case, fitted everything. We heard about like a lot about like solid suppression, so I don't need to like very much comment on what's happening here. So in metabolomics, it's quite usual. I'm not sure what they actually did, but I'm fairly sure they did pre-saturation here, because this is the #1 thing that they typically do. And we already heard like in Bruno's talk that lactate might be quite an issue. So you can see it should be 10, it is 2 here, and it is 3 in the qNMR. So that likely this is something that's happening due to some influence of the solid suppression. But what we also seen is that we are much better with our approach in case of like the formic acid, acetic acid, and citrate. And we were thinking about why is this the case? Why is this happening? And basically, we thought about like, hey, there is no line width estimation in qNMR here. So we might have some influences here on this optimization problem. I don't know why this is not adjustable there, but it seems to be not. So we're actually getting quite decent results here on this metabolomics approach. Of course, this is not like high accuracy qNMR. This is more like on this metabolomics approaches here. But we're getting, from like comparison of the state of the art that people are using in metabolomics, we are reaching even like some better results here with our approach. Another thing, I mean, we hear a bit more about like quantum mechanics and later on in this workshop, so I don't want to get into like much detail here. We are back to like this benchtop NMR application of our reaction, and we thought about, okay, what's going to happen if we have some species that we cannot isolate, so we cannot have a pure component. So where do we get this information from? And one example was a lithiated reagent, which is only happening in the reaction itself. You cannot really isolate this. So we teamed up with some colleagues doing quantum mechanical predictions, and we got this from the quantum mechanical, like based on the structure of it, from the quantum mechanical prediction. And the easy thing that we did, we just basically generated a line width onto it and did run the optimization from there, which worked really well. But you can see there are much more lines here, because I mean, we get every single line from the quantum mechanics. So this is a much higher computational effort. But in case you cannot get a pure component, this would be also one option to start from the structure instead of having an actual measurement from needed to actually do this indirect hard modeling approaches. And the last thing I want to comment a little bit is like what's going on with machine learning. So we tried to do machine learning on it with some colleagues, and I always a bit curious in this, like, because we are not talking about big data here. And for training of these machine learning models, typically you need a very large data set, which we typically don't have. Even if we think we have a lot of data, compared to some examples from like IT, we don't have a lot of data. We're still like in a small we have like very good information on our data, but we are still on a small data set. So what we try to do to get started with this is some kind of like thing like augmentation. And if you compare it to some things which are more common to like neural networks, which would be image recognition, you can see a data set of some pet pictures here, basically dogs. And what you would do with augmentation is you take one of these pictures and you add some variety under this data. Like, for example, in this case, like turning it around, messing with some colors, messing with some other things on the picture to get a more extended training set. And if we transfer this to what we did with the NMR spectrum, we took our pure component data from 300 NMR spectra. And what we did basically is we inverted our process of this indirect pattern modeling by moving the position of the peaks in one of our like first procedure, and in the second procedure, moving the position, the width, and the height of the peak. So basically inverting what we did in optimizing the indirect pattern modeling to get a larger data set and to increase the data set by a factor of 1,000. So we took 300 spectra in there, and we ended up with 300,000 augmented spectra to train artificial neural networks and to get an information about the component concentrations here. And this actually worked pretty well. So if you compare it to our indirect pattern modeling approach, we get some similar results in the mean square error values here. And you can also see these plots are looking very much similar between these two approaches with the neural networks and our, like in this case, as a benchmark, our indirect pattern modeling approach. The advantage of this, which is not really an advantage for like our metrology applications, because we typically have time to do things. But here you can see this is a factor from 10 seconds to less than a millisecond in getting the prediction done in between like calculation power when it comes to like this. So you can do, if you do some real-time applications, you can really do advantages like running these neural networks, because you can do like, for example, 100 different models applied to the data in the same time that you would do one of these more computational power indirect pattern modeling. But of course, as a disclaimer, when you mess with your basis data set and you mess with data augmentation, you need to make sure that this is reasonable data that you deal with. So we know that messing with the position, messing with these things can happen in the NMR spectrum. So it is reasonable to do that, but of course it's not covering the whole range what can happen. So in case you're messing with the basis data set, the model is always only as good as the training data. So this is something you need to always have in mind when you're running with these more advanced spectrum modeling approaches. So I wanted to show you some like that deconvolution can improve results in complex situations. If you have an easy situation, there's no need for it. But if you have complex situation like crowded spectra, artifacts, overlap of signals, this can be a valid option to consider. And it always depends on the application. So you always have to get into the spectra and see what kind of model or what kind of spectra you see and what kind of like method you want to apply to it. If you go for spectrum modeling, it's always just as good as the training data, and you need to spend a lot of time training these models to get accurate results here. But benchtop NMR spectroscopy fosters a lot of like development of applications using this deconvolution and modeling approaches, because you just simply can't just integrate the signals. But always question suitability and always perform validation of these models with some known samples of some known concentrations to actually get some feeling for it. Of course, I haven't done this all by myself, so I have to thank a lot of like colleagues at BIPM, also at CHERM, and also like my fellow like co-authors of qNMR handbook. I took some pictures from it here, and also some companies. And we have like a lot of like qNMR experts here, and we're talking about some more advanced techniques. I wanted to because a colleague asked me to pitch something here, and I wanted to use the opportunity to maybe present you something. What we are working on some nanoparticles with qNMR, which is a very interesting thing. I just recently joined at BIPM. They asked me to present like maybe 2 minutes here. This goes on like functionalities on nanoparticles, which is an ongoing project, an EMB project. And we did some work together with NRC Canada on that to get some traceable results on functional groups onto silicon nanoparticles after suitable sample preparation step, and there are some interlaboratory comparisons planned, and my colleague will also pitch that tomorrow in the surface analysis working group, and they seem to be quite interested in potential pilot study running this kind of things to get some reference materials on these functionalized nanoparticles. And of course, like surface analysis working group has no qNMR at all. So this is where we might come into play. So if you are interested in getting more details on this, please come to me and we can talk about this later on. So you can see this is some preliminary work that was already done in optimizing protocols and comparing it to some titration approaches that were already in place to compare it. You can see pretty good results here to the potentiometric titration. And the idea is to get some traceable values for reference material production onto this nanoparticles. So there will be an interlaboratory comparison later this year in the Versailles project of Advanced Materials and Standards, FAMAS. I just recently heard about this myself, so I don't know if you're aware of it, with 3 different nanoparticles and different sizes and different factor of like these amount of, in this case, amine functions. So we can, if you're interested in this, please find me. So we are happy to include more people in this qNMR approaches. From the qNMR measurement itself, in my opinion, it's very easy. It's when you look at the spectrum, you can integrate these peaks and you get the information. It's more about the protocols, getting the samples at the stage where you can do the measurement. Yeah, with that, I'm at the end. So thank you very much for your attention. And yeah, I think we can have questions now. We can have it after the lunch, after in the next official roundtable discussion after this session. So I don't know what the time.
We probably have time for a couple of questions or
okay,
a few
perfect.
questions. So I have a question.
Yeah, sure.
How would you say the indirect heart modeling approach compares to qMSA with regards, especially with regards to dealing with potential digital standards and moving to different views, because that is something that is being done with qMSA, but is that even possible with indirect modeling? Or
I mean, it would be possible, because basically what we are also like trying to do with indirect heart modeling in this reaction monitoring approaches, because we want it to be more flexible. And NMR as a process analytical tool is very flexible when it comes to like different like reactions on the same setup, for example. So what we try to do is like getting our pure components in a kind of like database and then clicking together this mixture model on the fly, because a lot of this chemometric modeling is very tedious when it comes to calibration. So you need to start from the scratch. So you change something on your process, you need to get all the way back to the front and like do some new modeling. And this is where the indirect heart modeling is very nice, because you basically combine, and for example, if you find a new component, you just add it to your model later on. Or you find you're changing something of your chemistry. We did that with changing some of the substituents on these aromatic signals, for example, and putting it into the model, and it works quite well. And you can also do the same combined with the quantum mechanical calculations, starting from the structures. But of course, this would be quite tedious when it comes to computational power in the first place to get this done, because of the large number of these signals here. But of course, you can always also try to simplify it, because I don't think you need to have all the lines modeled at the same time. We just did it here. So you can also maybe just do some peak grouping and things like this to optimize computational power in the end. But I think this is the same, it's getting into the same direction like this digital reference materials, because you want to have basically like a database you can count on, and you can just use and apply to your spectrum in the end. And I'm fairly sure that you can also do this indirect heart modeling in the same way, or even combined with this in a combined fashion, yeah.
all right, folks, so it's 2 p.m. already. We're gonna resume our workshop with our presentation from Eli with LGC, not LGC, the NML and in the UK. She's gonna be leading us into the discussions or continuing the discussions for our third session today. Thank you, Eli.
Hey, good afternoon, everyone, and thank you for joining this presentation. Today I'm going to be presenting different ways we can measure uncertainty using deconvolution. Good afternoon, everyone, and thank you for joining this presentation. Today I'm going to be presenting on measuring uncertainty using deconvolution methods. Firstly, I'm going to go through an outline of my presentation. I'm going to talk about why it's necessary for us to use deconvolution and the software that we've been using within our own team to apply the deconvolution, different contributions of uncertainty that come from deconvolution, and different ways we can estimate the uncertainty of deconvolution. In the end, I will conclude with the approach that we will take within our team. Okay, so why is it necessary for us to apply deconvolution? So as we get more complex samples and larger molecules and mixtures, we have more and more crowding of our NMR spectra, which leads to more and more overlapping peaks. And then it's not clear for us to pick an analyte peak, which we could integrate without correcting for. So one way we could work around this is by using deconvolution. If we do use deconvolution, we then have to consider the extra uncertainties that come with this. So here I have an example of an analyte which has overlapping impurity peaks. And one approach is we can correct for it by manually integrating the impurity peaks and subtracting this away from the analyte to get the area of get the purity value for the analyte peak. However, this could be overestimating the area of our impurity peak and underestimating the purity of our analyte peak. So with the application of deconvolution, which adds a line fitting function to better resolve our overlapping impurity peaks, we can potentially have a better estimation of the area of the impurity peaks and have a better purity value on our analyte sample. So within our team, we've been using Metronova software, and Metronova has a function called global spectrum deconvolution, which will deconvolute your whole of your spectrum for you. It uses a generalized Lorentzian function. Typically, you would apply your global spectrum deconvolution first, and then after this, you can apply your quantitative global spectrum deconvolution, which just better refines your line fitting peaks that the GC has already done. It will also minimize the residuals, and it is computationally more intensive, requiring an extra few minutes for this to be applied onto the spectrum. However, the line fitting is more superior and better for quantitation. So when it comes to selecting appropriate spectra for your for applying deconvolution, you need to have sufficient separation. You can't have a situation whereby your impurity peak and your analyte peak are 100% overlapped, because this makes the line fitting function really difficult to pick that out. So we need to have some type of separation. You also have to have really good line shapes through your replicates that you run and your iterations. If your line shape varies through your repetitions and your iterations, then that's going to lead to a higher uncertainty. Also, Metronova have recommended that there should be high digital resolution, at least 64 KB. Okay, now I'm just going to quickly highlight the established uncertainty that we already have for qNMR. This takes into account how we prepare the samples, the sample weights, the data processing information that we analyze in the internal standard, and we take the root sum of squares to combine these relative uncertainties. So we already have an established uncertainty budget for qNMR. What we want to do now is determine what the extra uncertainty is coming from the deconvolution processing step. So I'm just going to go into that next. So additional uncertainties that could be coming from deconvolution is how overlapped your peaks are. The greater the overlap, the higher you'll have for uncertainty. Also, how many overlapping impurity peaks are you considering? If there's loads of impurity peaks that you're going to be correcting for, you're going to have higher uncertainty. Also, you have to think about your processing parameters that you'll use and how this is going to be affecting your line fitting. Another consideration for the uncertainty is your residual curve. The larger the residual curve, the more uncertainty. The residual curve tells you the difference between your experimental data and your line fitted peaks. So the larger that is, it'll have an indication that the model didn't fit so great and it was a poor fit. And then lastly, your line shape has to be consistent throughout your experiment, and variations in this will give you increased spread in results. Okay, so we looked at several different ways of trying to determine the uncertainty of deconvolution. One way we looked at was looking at the parameter effects through the use of a fractional factorial design experiment. Another way we looked at uncertainty was looking at the residual errors. And finally, we looked at the corrected line fitted impurities. So I'm going to go into a little bit more detail about the uncertainty estimation for the parameter effects using the fractional factorial design. So what is a fractional factorial design for those who don't know? It's basically a really good statistical experiment that will look at your different parameters within your deconvolution and look at their effects and interactions. Within our team, we use the resolution 4 fractional factorial design to try and estimate the main impacts from the different parameter effects. So why was the resolution 4 a good option for us to choose? So we can identify the parameters within the deconvolution that are most significant in the deconvolution processing. It also reduces the number of trials that we run, as this is a fractional factorial design. We don't have to run the full factorial design. So it will save us some time and resources. Also, it's a good way of being able to quantify uncertainty through how different processing choices influence your results. And also, this could be a robust way of determining uncertainty, as this method is resilient to variations. So for the resolution 4 fractional factorial design experiment, we identified 4 different parameters, and we varied them under reasonable extreme variations. So the parameters that we looked at was the baseline fit method, different zoom regions, the refinement levels of the GSD fitting cycles, and then also the improvement cycles from the qGSD application. And we just varied these different parameters for these functions to look at how it would affect the final result. So we had 16 runs on this fractional factorial design that we applied using the different baseline methods and parameter variations. So how can we quantify uncertainty from the different parameter effects? So one way we can do this is we can take the mean of the low and the high of the different parameters and minus them from each other to give us the effect. So this is what we did for the baseline fit. We took the mean of the ablative and then the mean of the splines. We minused it from each other, and then that gave us 0.57 as the effect for the baseline fit. Here is a summary of all the other parameters and the effect they had. Here I have a confidence interval plot for the deconvolution parameter effects. As you can see, the biggest effect came from the baseline method, which is furthest away from 0, making it statistically significant. So the baseline fit will have the biggest effect on your line fitting peaks, followed by the refinement levels. Okay, so how can we determine the uncertainty from this? So there's 2 approaches we can determine the standard uncertainty. We can treat this as a rectangular distribution, or we could use the standard deviation of the experiment. So if we go with option 1 and treating it as a rectangular distribution of the standard uncertainties, we have to use the formula shown on screen. So we take our effect and divide that by the square root of 12. So we did that for all the different parameters that we had, and we got our standard uncertainties from that. And once we had our standard uncertainties, we had to combine them together by the root sum of squares. And then we have done this, and then we get our final result of 0.17. So even after combining, it was interesting to see that this value was the same number as the standard uncertainty that we had for the baseline fit, making the baseline fit the most significant value, and the other parameters were not as significant. Okay, so now that we've got our standard uncertainty, we can convert this now into the relative uncertainty. And to do that, you just take your standard uncertainty over your measured value times 100, and then we got the value of 0.086% mass. The other option was to convert the standard deviation of your experiment to the relative uncertainty. And to do that, you just take your standard deviation over the measured value times it by 100, and that gives you your value of 0.21% mass. Okay, so now that we have our relative uncertainty value for our deconvolution processing step, we want to now combine this with our already established uncertainty budget that we have. And to do this, you just do the root sum of squares and combine these two factors. And once you've done that, you can get your expanded uncertainty at 95% confidence just by taking that value and timesing it by k. All right, so there are some advantages to using this way of determining uncertainty. It's a statistical method. It looks at all of your different parameters, and it looks at what effects your different parameters have and can vary them. Also, it's a reliable way of determining the uncertainty value and can be combined into your qNMR uncertainty budget seamlessly. Also, within the deconvolution, when you're doing your integration, it does already account for your impurity line-fitted peaks as well. Some disadvantages are that it takes a lot of time to process all of the different fractional factorial design spectra. It can be expensive and it is resource intensive. Also, because this is only a fractional factorial design, there could be some parameters that we didn't include, so it could affect the overall uncertainty estimation. Okay, so moving on, now I'm going to talk about uncertainty estimations from the residual errors. So the residual errors is the experimental line minus the line fitted peaks, and it can reflect how good your deconvolution model was. And it could be a direct way of estimating the uncertainty, with larger residuals indicating a greater uncertainty. However, Metronova software provides you with the residual error value, but it's unclear exactly how they get that value. So we were limited in further investigation into that type of uncertainty. Moving on, so uncertainty estimation from corrected line-fitted impurity peaks. This is where we correct for our line-fitted impurity peaks and account that for the uncertainty. So we can't take the standard uncertainty of the line-fitted impurity peaks and convert it into a relative uncertainty and include it into our already established uncertainty budget. So we can't do that. So because we've corrected for the line-fitted impurity peak, and to do this, there was a subtraction operation. Therefore, it has to be treated as an absolute value. So we then have to follow the formula shown on the screen. Take the line-fitted impurity away from your analyte, and then once you've got that, then you can combine your established uncertainty with your impurity uncertainty separately to get your final uncertainty for if you do the line fitting correction. The advantages of using this type of uncertainty is that it's a clear way, it's a quantitative measure of the variability. It can be a robust way of estimating the uncertainty when you're correcting for the analyte and measurement. And it can also indicate if your model performance was inconsistent or if it was poor. Disadvantages are that if you have already selected the incorrect model from the beginning, it's going to distort your uncertainty estimates. Another thing is it's really difficult to convert it back into relative uncertainty percent, so you can put it back into your established uncertainty budget. You have to treat this type of approach differently, which can take up more time. Also, you're only going to be looking at a fixed parameters of your deconvolution. There won't be any variation. And as I mentioned earlier, your deconvolution already takes into account your line-fitted impurity peaks. So if we're going to correct for it again, it could be double counting. Okay, so in summary, from all the different types of measurement uncertainty approaches that we took, we recommend using the resolution for fractional factorial standard deviation approach. This provided the most reliable uncertainty estimate for the deconvolution processing step. So how can this now be implemented? So what we're going to be doing is we're going to make it more resource effective so it doesn't take up too much time of the analyst. We're going to redesign the fractional factorial design so it's specific for the particular spectrum that you're looking at. We're also going to try and decrease the number of runs from 16 to 8. This will cut, hopefully, the processing time in half. And we're also going to make a validated spreadsheet, so it already has all the calculations for the deconvolution processing steps in there. So all the analyst needs to do is just put in their integral values, and then they can come out with the final answer. So in conclusion, we looked at many different approaches to determine the uncertainty of the deconvolution processing step, and we came up with the resolution for fractional factorial design using the standard deviation option as the most comprehensive estimation of the deconvolution uncertainty. It's a systematic way that evaluates different parameters, their effects and interactions. And it can provide you with a reliable uncertainty, which you can add on to your already established uncertainty in a seamless way. I would like to thank our Chief Metrologist, Stephen Ellison, who has been fantastic. He's a genius in statistics and really knows a lot about uncertainty. I'd also like to thank the protein calibration team, particularly 𝐏𝐫𝐞𝐬𝐞𝐬𝐈𝐧𝐬 for all her advice throughout this project and her support. And I'd also like to thank Nostranova and Pablo, particularly, who answered loads of my questions about the software and how it works. Thank you for your attention.
Okay, so we have time for questions, if we have questions for Ali.
Maybe, right? Yeah, on the fractional factorial designs, can you comment on how you can maybe automate this to get like a little less user interaction?
So to automate the actual spectral processing, so you can't do that. You will have your designed fractional factorial design, and then what you have to do is you have to vary the different parameters accordingly, but you will have to do that manually yourself.
But can I mean, I'm not an expert on like ANOVA scripting language, but I guess you can interfere with the software pretty deep. So you could also have some kind of like automation going on and scripting that changes this for yourself, so that it would save a lot of time. But it's tedious to do that.
Then that's going to add another uncertainty of how it's doing that, and that would be an extra consideration that you have to take in. Is it doing it exactly how you want it each time, and how are you going to check for that?
Okay, I mean, we can talk about this later. So like, I think you can do it. Like, of course, you might have some influences of this, but I think you also have some influences when you do it manually all the time.
Yes, exactly. Yeah, but we did look at that option, but we thought that would just introduce more uncertainties. So we thought better way was just to reduce the number of runs in the fractional factorial design. If we can get it up to 8 runs, then that will already halve the time that we do it. And if we already have the validated spreadsheet, then all you have to do is just put in your values and the calculations that will be done for you. So that will also take less time for you as well.
Thank you.
Just to add to that, you can do a lot of automated processing in Nostranova. So I think you could potentially do that.
Yeah, no, the scripting is not so easy to learn. So I tried this when I was with Magnetech and doing some automated routines with it. So it was not so easy to get a feeling for how to operate. I mean, Nostranova will always tell you, yeah, it's nice, you can do everything with the scripting language, and then you look at it and say, okay, I did some basic programming, but this is different. And the documentation was also not that straightforward, in my opinion. Maybe it's changed in the recent years, but.
Yes, so welcome everyone. I'm Dr. Karen Robertson. So I started from the BIPM last June, and my talk will nicely kind of visit a lot of the talks and discussions that have already happened. So I'm quite happy that I'm coming later in the day. And don't worry, I'll try not to focus too much on quantum mechanics equations and kind of look at the application areas and where those, as Maria was saying, the gaps could be filled with different research. So as I said, I'll be kind of giving a brief introduction about the quantum mechanics and NMR, progress in this area from the 1950s up to now, where computational power is assisting us in these efforts. A case study that we're using at the BIPM currently for metrology applications of it. And again, obviously, this was some of it was previously discussed, the methods being used. And in further applications that are being used in different areas. Alongside this, then, how the use of quantum mechanics and NMR can be supported by AI and machine learning, deep learning, and then how they can complement each other kind of in the area of metrology and developing methods. So fundamentally, NMR peaks and spectra, they're defined by spin parameters of the nuclei spin of molecules. So when we think of it mathematically, these are modeled by Hamiltonian matrices. So to summarize that, it's essentially a mixture of the lattice, which is looking at the chemical shift affected by the environment it's in, the spins that are being interacted, and then other interactions terms within the system. But we would need to model all these interactions if we're looking at the mathematical model. So if we're looking at then things with the eigenstates and energy levels, which determine the resonance frequencies, we'd be looking at this equation. And then obviously we then need to simulate the responses, which would be looking at the FID that's generated. So all of these calculations of equations is how a lot of these spin parameters be determined through the quantum mechanics of the system. You then obviously have to then look at the intensities and relaxation behavior of the NMR signals, but then obviously from experimental data, this is more relevant when we're looking at ratios of internal standards to analyze. So this is more looking at kind of the energy conservation and the quality of how NMR data itself might be different to what the method-derived data is. So trying to get the matching of the two data sets in the theoretical to the experimental to be as close as possible. And this has been done not specifically in an NMR, but in magnetic beam curves as early as the 1950s, where a theoretical curve was being compared to experimental. Here for a very simple model for the hydrogen and hydrochloric acid, where they could, from the mathematical derivation, they could get quite reasonable matching for the experimental curve to the theoretical curve in a magnetic beam experiment. So when we think of it, we want to think of some key points. So obviously quantum mechanics can achieve a complete understanding and quantitation of NMR spectrum. This is due to obviously being able to identify all the spin parameters of each individual spin. So if there's signal overlap and higher order effects, these can be derived. So in the previous talk about deconvolution, this was mainly looking at signal overlap, but then higher order effects, deconvolution does struggle with that. NMR spectra can be fully calculated, and this is from the Hamiltonian matrix I showed, where we're looking at chemical shifts, coupling constants, and alignment values, which allows us to be intrinsically quantitative when we're looking at the values determined. However, there are some other elements that when you think of a phenotypic interpretation of the NMR spectra from experimental data, they're actually taken out when you're just considering the spin parameters. So you are actually simplifying the data when you're looking at a quantum mechanics approach, even though that does sound a bit backward in that you actually are simplifying it. This also means that if you're getting these simplified data, they are field independent. So this potentially means from Klas's talk on benchtop NMR and how high field NMR are more commonly used in proteins, they can actually be worked in tandem to aid each other in developing different methods. So I'll speak a bit later on about potentially using, say, external calibration method and methods like that, where another NMR is used to improve the results of potentially lower field NMR through reference spectra. And then also we need to look at determination of the relative intensity. So that's looking at observed and theoretical and separation, where integral use here obviously requires careful consideration of where you're placing them. But if you're separating every single signal based on spin parameters and these defined chemical shifts in coupling constants, they're not going to be overlapping because they're two individual variable value data sets that won't be obviously, as we say, more a genotypic response where they're actually separate entities. And again, just going back to the generic deconvolution, where it would optimize a larger number of parameters for each spectral peak, but qMSA optimizes parameters of each spin particle individually. And again, that leads maybe to the higher computational requirement as such. So when we look at kind of summarizing everything I just said there and what we want to look at and comparing it to the other methods here. So obviously for NMR spectroscopy, different mathematical models can go beyond the kind of from foundation models. But then for more established theory, we want to be able to calculate the actual NMR spin parameters that were being tested in here. So when we look at the electronic system of a molecule, all the transition energies, relative line intensities, they obey these laws of quantum mechanics that I previously outlined, and therefore can be calculated. However, if we're thinking of saying deconvolution, line fitting, and things like that, or predictive models, these can work kind of in tandem to aid in this. So if we see down here in the experimental spectra, we can do quantum mechanical analysis, but some systems will actually use predicted spectra to do this quantum mechanical analysis to then derive the Hamiltonian model to get a spectrum, which can then feed back to the iterative spectral fitting here. And then on the left, I just show the kind of what I mean by deconvolution versus quantum mechanics. So the higher order effect I mentioned there is the deconvolution will kind of categorize these all as the same type of order, and they'll identify them kind of as one unit. Whereas the what I mean by the spin parameters being defined here, they'll actually define them as individual entities, and then you can group them here. But again, that suggests to obviously higher computational requirements for these elements here. And this kind of summarizes where we're at with the computational power. So this was from a kind of publication this year. I think it was a couple of weeks ago, where they actually looked at the power of computers. So from the 1950s, where they were able to obviously derive some of these spin parameters, and how many number of spins are actually being able to be identified now in the size. So as previously in the discussion, we were discussing what size of peptide could potentially be looked at with quantum mechanics structural analysis and the computing power required. But currently at the moment, we're looking at molecules of this size. But obviously with the potential of quantum chips and more supercomputers coming in, that is potentially going to be helping more. And the dependence on magnetic field, we can see doesn't draw too much relationship to what the number of spins can be computationally calculated. So again, it is more dependent on the computing power as seen here. So that's where quantum mechanics structural analysis does differ to other NMR methods, where a lot of the sins can be forgiven by increasing your magnetic strength, whereas here it's more about the computational power. So what we've been looking at the BIPM, and one thing that's gotten a lot of interest from specific groups, and I'll discuss one group that's quite relevant here, is 1H iterative full spin analysis. So a lot of these are now server-based solutions, and they only really require a couple of inputs from the user. So again, you have your experimental spectra and then your structure of the molecule. And with that structure, it can predict a kind of starting point, and then it can start doing the different steps. So it will analyze your spectral data by performing peak picking, complete spectral deconvolution, and line shape estimation. So these are all done by potentially different models or algorithms that are being used for the software or the different packages used. This then can also generate 3D representation of your molecular structures just for visualization purposes, and then allows you to look at your chemical shifts, coupling constants, again, what has been derived from the quantum mechanical methods there. So again, we're kind of moving through this cycle again where the workflow can then compare in the bottom section here, and you can do some manual corrections yourself to aid in that spectral comparison, because obviously you might have different elements that the quantum mechanical system's not going to actually know, because it's not relating to what the phenotypic interpretation of the data will be showing. And then obviously we'll have an optimization, minimization process where you have the multiple iterations moving through, where the fitting is trying to get as close as possible. So the final output, kind of in a generic phrase, is perfect fit, where you can then, instead of looking at an integral kind of approach of your analyte and internal standard, you're getting a ratio approach, which can then be calculated and give you, say, purity values from that understanding. And then also, if you're looking at, say, larger molecules or polymers or proteins, that quantum mechanics fit can help to aid in understanding dihedral angles and elements like that. And again, obviously, I've already spoken about manual optimization if you've got some suboptimal results within the system. And one thing that I want to point out is that last year, USPID was released. So the one system we're using at BIPM is something Klas mentioned, which is Cosmic Truth by Matthias Niemann. But USPID was recently released by Metrology Research in line with USP. And what that does is it takes predicted data sets of digital reference materials from their library and uses that as a kind of starting point. So that reduces the initial starting computational power requirement to then do this qMMA element here. There is also other algorithms that are being developed from different groups. So it does seem like we're at quite a good stage where in the last couple of years, this is really starting to gain speed, especially in the metrology area. So we're at quite a good point. We're not too far behind. We're in it. So it's good that a lot of attention is being placed on this here. How does this relate to what we're trying to achieve at the BIPM and obviously within the CPM and the CCQM? Is looking at the activities of the BIPM together with NMIJ and other expert NMIs, is looking at the different reference materials that have been validated, verified to use as internal standards. So obviously they've been released over the last couple of years in open access guiding documents on the best standards. So this has been called the qNMR Octad, which is now kind of a non-ad because of what Wagner talked about, the fluorine based element that's been added here. So that plays two roles. And again, obviously talking about how 19F qNMR is starting to take a real boost. And we're looking currently at new 19F elements to add to the octet to make it further tags on the end to add more elements there. So where do we think that qMSA-based methods fit in here? So one thing we want to do is obviously use these internal standards that have the data, that have the ISRDs, that have all the data set kind of behind them, supporting them. How does qMSA evaluation compare to what's already been done for these materials? So with Gustavo has set up during COVID, looking at data that was already acquired and running it through the qMSA software with the support of NMR solutions to investigate, obviously, the comparisons there. So just to give an understanding of how the Cosmic Truth software works on the left compared to the traditional manual integration methods. So the main differences are highlighted here. So as I've said previously, the spin parameters are collected and then these are matched. So we, again, like the deconvolution, we'll get a residual in green down in the bottom left to show matching. And then you get a score of the matching up here. This matching is very good. It does seem to be very good, even though there is quite a large residual for what we want to see in the metrology area. And they do give a quality level assessed as an output as well. But the main thing to know is the molar fraction internal standard is looking here. So that's kind of looking at what is the ratios of these to each other. So what is the ratio of one to the other? So if we look at the maleic acid and D2O ratio compared to the KPH and D2O, we can then determine the purity standard from this calculation here. So then when we look at the traditional method, this is looking more obviously integral and in number of protons. And then it uses the same elements here of the equation to get the final value. So this is just showing kind of the different methods used and how there is a bit of variability there, which has to be considered. So the work done on these two model systems of DMTP with D6 and maleic acid with KHP and D2O. So this has been done over multiple years by Gustavo and Matthias Niemann since 2020 to improve the algorithm and train the system on this. So again, obviously, when it was first done, there was some issues in baseline correction and phase of water signal issues. So again, looking at potential suppression efforts and improving spectral quality or normalizing of spectral quality for what the QM would expect to see. And this is illustrated as well if you're using a decoupled experiment, you're getting a much better uncertainty, but you're getting a much higher overestimation of the data. So you've kind of got something that's within the uncertainty, but then you've also got another result that's got lower uncertainty, but is well away from the CRV, purity reference value. And obviously, as you start doing more optimization, you're reducing that uncertainty, but you're still getting a value that is underestimated. However, what was developed by them was a kind of guided integral algorithm selection, where they used the integral that they derived from the data, was then made independent of the other variables within the effects, the variable effects of the acquisition. So that's just where we're looking at these elements that start to improve what's being shown within the system. So this is called the QM guided integral selection, where the integral that used by the QM for the ratio was guided by the initial experimental data to be able to get value that was closer to these values here. So again, that does need to be tested on more models to actually say that that specific algorithm can work across models. Because if we're saying this has been tested on this model, yes, we can say it works for this model, but it needs to then work for other models, because you could just be essentially biasing it to the right value, and you haven't done it with other areas. So again, just looking at kind of the issues with manual integration and what causes potential uncertainty into the system, and then what we can see as being positive aspects of the different elements. So what's currently being done, as I said, is looking at more of the Octad model systems to kind of validate that new algorithm that they've said, the guided integration. And then obviously the potential for other modules to be evaluated and data sets to be made available to other software companies is something that would also be potentially linked to the previous discussion, where pilot studies being done where publicly available data could just be made available to these, not so maybe we don't have to do it, so they're able to do it themselves to then benchmark against what we are getting for the key comparison values and what they're then seeing with their software, and allowing a bit of competition between them to see how their algorithms will work in purity assignment. And then also looking at AI machine learnings, because the main thing that was driving this discrepancy between values and uncertainty was this residual values here, as previously talked about in the deconvolution uncertainty measurement talk. So can we investigate the use of AI machine learning, deep learning techniques to improve the enhance the experimental spectral quality to essentially drop this residual down here to a flat line between. So the matching is then perfect between them, which would then put this value without the need for augmented algorithms to this value here. So you could almost use the initial starting point, and that would be giving you much closer and much lower uncertainties in this system already. So this is just some other examples, which I think actually lines up quite nicely, where we were talking about peptide usage, and this goes more to maybe what POG is looking at. And so here we're looking at use of QMSA for representing oxytocin J couplings, and then comparing them versus what they look like in their own systems. So how they differentiate between secondary structures, and how they differentiate between the different forms, so alpha or beta amino acids, and then obviously looking at their J couplings to one another and the difference between amino acids on their own. So if you're trying to characterize peptides and the amino acid values are different on their own to what they're in the system, then QMSA has been used to show these differences, which will help and guide the characterization of the user. And then something that goes more to what Bruno was discussing about external references is looking at potentially digital reference standards. So I know there's Hemi's twin, which Merck is pushing now a bit more. I think they released it last year to users, and they're looking at 19F as well, potentially. But something that this does is that actually with the qNMR will allow the kind of field independent quantitation through the DRMs that are being provided by different providers. So again, that kind of link between the low and high field and what we're trying to achieve with those. So again, kind of working in tandem with different groups or areas that have higher field magnets supporting potentially groups with lower field magnets through the NMR research community. So now moving on to the artificial intelligence machine learning, it's a bit shorter, but a bit more snappy because it's mainly looking at the applications and what we could propose to do and potentially have discussion after, but there was a bit of discussion previously. So it kind of takes different flavors of artificial intelligence, machine learning, deep learning. So the one on the left is a little bit simpler. So it's a spectrum of pure compound, spectrum of mixture. They go then into different neural networks, and they essentially will then be used similar, if you think of the visualization where you've seen the individual spectra of each one being fitted, but using the AI machine learning to fit that. Whereas on the right, we look more at a protein-based analysis where this has multiple AI algorithms, multiple nodal frameworks within it to do different steps throughout the system. So again, these are two kind of flavors of the same basic principle, but with varying degrees of complexity and what's trying to be achieved here. So for a quantitation metrology perspective, the one on the left is more useful, which is good for people in the smaller organics group, but then the more complicated one on the right is where there's looking at characterizing the structure and activity of proteins using these elements. So you can see how 2D, 3D, 4D NMR can all be implemented into the different elements. The data can be improved, the data can be analyzed with peak picking, deconvolution, unfolding with the data for quality. It can then be iteratively improved or iteratively changed, and going through all those steps to then assign the spin systems of the different elements of your protein, and then can go to different refinements to feed back into the loop. So again, this is a lot more time-intensive, computationally intensive method. However, it can aid in what's moving forward forward. And this is for the Artina workflow, which has been, I think the last couple of years been published, and they've got a software attached to that, which does all these steps. So going again, just summarizing kind of what is useful, maybe a bit more at the moment for pre-acquisition. So this is looking at, Bruno mentioned WADE, the water suppression experiment. So here I've got another one called Genetics AI, which just has a fancy name. But essentially that's used for more complex protein-based experimentals. So an experiment called TROSY, and that's trying to optimize the different timings in the pulse sequence to get the best signal to noise when you really need it for low concentration protein samples and more disordered protein samples. But WADE is a good example of a pre-acquisition experiment design that can be more used for solvent suppression. Post-processing wise, we have Deep Picker, which is used for peak picking to identify which peaks are peaks of the same multiplet. Denoiser, which I'll talk a little bit more about, something like that. And then non-uniform sampling reconstruction, which is based upon non-uniform sampling, where you sample less of the data experimentally and calculate more of it computationally to reduce experiment time requirements, but still be able to try and get the same quality spectra at the end. So there's different domains that these come in, but JTF-Net is quite good in a way because they also published they also looked at assessing the quality of the AI-enhanced spectra, because they wanted to have a spectra that didn't require full sampled spectra, because if you're having to acquire full sampled spectra to assess the quality of your NUS, non-uniform sampling reconstruction, you already have the full sampled spectra, so why have you bothered doing the NUS reconstruction? So looking at the assessment, you look at different measures shown at the bottom here, but the requirer algorithm that was set up for the JTF-Net NUS reconstruction, that can be potentially reworked to try and look at quality assessment of other areas. And then obviously when we're looking more at, say, inter-laboratory studies and improving and normalizing data across the piece, we need to look at obviously magnet stability, shimming, vibration effects, sampling artifacts, and again, the solvent suppression, inappropriate volume choices, where again, if your peak shape is different, then you could have issues on the end. Again, peak overlap, and then obviously if anybody's looking at statistical analysis of the data as well, involving that. So something for now that we're investigating, or I'm investigating, kind of wanting to look at, is spectral quality enhancement algorithms. So something that was in a recent Polish NMR workshop was an open access program called ShimNet, which had this lovely picture that I'm hijacking to look at training, obviously of calibration samples, and then they purposely make a poor spectra for the shimming, and then they can actually, for a trained model, enhance the spectra and normalize shim. So again, dependent on the user's skill or automation, you can almost get old data that maybe is not as good, but you can then try and enhance that. So old data could be enhanced, and then that enhancement can be compared to what the previous data was showing as well. So again, using data we've already gotten to look at the quality checks of these enhanced data sets. So again, another one was I mentioned was denoising. So if you've got raw noisy signal and you're trying to get your signal to noise up, so obviously going through these different networks and modules and nodes and learning to essentially train something on estimated noise, or potentially there's a way, if you think of it, if you get a perfect spectra, then you artificially add noise to it and you train your model on that, then you can get a denoise signal because it knows when noise has been added. So noise being added by the system instead of the user can then be estimated and removed by the system. So again, but this is something we need to see. Does this denoising happen uniformly across the whole spectra and the FID, or is there potential for it to actually affect the system? Again, and going back to maybe something more in the future to consider would be experimental design and optimization for this genetics AI and the WADE example that Bruno used as well, and looking at improving the purity assessment and purity profiling workflows across interlaboratory studies, potentially who do not have a NMR spectra expert in place, or who might be using NMR facilities outside of their organization to get the results, where they need to have something implemented which can then run and get the same quality of data as other groups. So something I just wanted to look at for this is the kind of epoch of AI and experimental design was in around 2019. So we see that the genetic algorithms being used have been slowly progressing, but then the artificial neural network experimental designs have only really started coming in 2019. So again, as I said previously, we're kind of at a good stage in time when we think about the QMSA and then this, that we're still within that timeline of kind of we're in the crest of the wave. It's not kind of crashing down on us now. So we're in a good place. And again, just at the top, adding in there comparison validation. So if we're using old data that has all the kind of backing, as we said in the discussion, where they've got the impurity corrected values, they've got the other techniques, they've got traceability to other elements as well, using that to kind of give validation and determine uncertainty measures for these enhanced techniques moving forward. And then also looking at potentially this require quality control. So again, this is kind of a very sweeping presentation about all the potential methodologies moving forward. And I obviously don't expect them all to be done, but just kind of giving an overview where quantum mechanics and AI and machine learning could potentially be in metrology. So again, these are just the takeaways that I've discussed throughout. And yes, I'd just like to thank Gustavo and Matthias Nimitz from Cosmic Troop for aiding in this. Obviously, Gustavo for doing the work over the last couple of years.
Good afternoon. I'm Huan Yao from the QM team at NIM China. And first, I want to say thank you for holding this workshop. Actually, this is my first year from the qNMR team in our NIM China, and I have learned a lot from this workshop and your meaningful discussion. And I will try my best to introduce our recent works in qNMR, integrate with separation strategy, and its application across molecular size. And today's presentation is structured in 4 parts. First is to introduce the principle and the challenges of qNMR, and next I will introduce qNMR approaches integrated with separation strategies that NIM have developed. And the third part, I will introduce 3 case studies of qNMR in peptide and protein analysis. And last part is a brief summary of our perspectives. So the basic requirement for qNMR accurate purity assessment is that the peak for quantification need to be isolated from that of impurities. However, sometimes it's difficult to achieve for low purity compounds, especially for larger molecules like peptides. If there is a peak from an impurity overlap with the peak of analytes, the result would be higher than the accurate value. So to achieve effective separation between the interfering signal and the signal for quantification, the most straightforward approach is using high-field NMR to enhance spectral resolution. Also, we can combine with deconvolution strategy. And the other way is to use HPLC NMR hybrid techniques. So this slide present our violin intercomparison data conducted using the 800 MHz NMR. All impurities identified by LC mass exhibited no signal overlap with the analyte or internal standard in the NMR spectrum, ensuring the accuracy of the quantitative results for this small amino acid. That is an easy one. And as shown in this table, the intraday RSD is very low to be 0.05%, and the interday RSD is 0.071%, and it is the lowest RSD in all qNMR reports at that time. Chromatography combined with NMR is another strategy that can remove the impurity spatially, but with larger uncertainty. There are two traditional HPLC NMR methods. First is direct continuous HPLC qNMR, which can remove impurities but use a large amount of dew-treated solvent as mobile force. And another one is HPLC qNMR uses single signal separation, use a common organic solvent, but still need to use a large amount of deuterium oxide. So a serious qNMR integrate with separation approaches have been developed by our team to enhance the measurement selectivity. Through these technologies, accurate quantification of relative low purity samples can be achieved, and the sample target cover from small molecule drugs with molecular weight less than 500 to protein, maybe large peptide molecules such as human insulin with a molecular weight greater than 1500. So the first method is two-signal separation HPLC qNMR method. Our MACTIN B1A with 7 homologs were used as the analyze. And in this method, common solvents are introduced as HPLC mobile phase, and the mixture solution of the sample and the internal standard was separated by HPLC, and the only elute of the target analytes and the internal standards were collected in one nail well for qNMR analysis, avoiding the disturb of other impurities. So you can see from the right side, without the signal suppression, only 2 solvent peaks of water and extra-natural were detected by basic proton NMR test, and after applying 2 signal suppression method, signal from analysis were detected clearly. So the sequence for signal suppression we used is given by Brooker, and there are some key parameters include the number of suppression and irradiation, frequency offset, and the suppression strength that we optimize. For the results, the purity of our MACTIN B1A determined by this method was consistent with the mass balance method with a bias of less than 1%. But mass balance method requires many instruments together, taking about 2 days per sample. But in contrast, the TSS HPLC qNMR method only need about 2 hours. This time is much more shorter. And but the challenge for this method is that the signal disruption may be happened because of the solvent separation. So some novel separation sequence as Dr. Bruno introduced, and many comprehensive optimization is critical to improving the accuracy. For the cases of compound with lower purity, especially peptides, the impurity peaks are likely to incompletely separate from the peaks of mean component. So that will affect the true purity determined by qNMR. So we proposed a method named the 𝐏𝐵𝐞𝐬𝐞𝐬𝐈𝐧𝐬 𝐈𝐧𝐬 method. This method can remove the overlap peaks from impurities by produce a high purity calibration standard from the original sample. So this method can expand the qNMR method to peptides and proteins, and I will talk it in the part 3. So, but for this method, you can see in the key point is the purification process. That is step 1. A large amount of high purity samples is required to ensure the accuracy of the measurement result, which is sometimes difficult to achieve. So to solve this problem, ISRC internal standard recovery correction 𝐏𝐵𝐞𝐬𝐞𝐬 qNMR method was proposed. And in this method, a mixed solution of sample and an internal standard was separated by 𝐏𝐵𝐞 and the common mobile fields, and only the elute of the analyzed and the internal standards were collected in same tube. After evaporation and redissolution, it was determined by qNMR, which is the same to the last method, but the difference is a recovery correction factor based on the 𝐏𝐵𝐞 area ratio between the analyzed and the internal standard before and after the purification process was proposed. This factor can reduce the error from the sample loss. Our MACTIN B1A was used as the model molecules. You can see after 𝐏𝐵𝐞 correction with internal standard, the mass fraction of analyzed were constant, even though the sample loss varied during these procedures or even in bad resolution of 𝐏𝐵𝐞. So this method is accurate by excluding influence from structure similar impurities. Moreover, this method can also use for the establishment of traceability chain for other homologs of our MACTIN B1A based on LC DAD analysis of different homologs. As we can see for ISRC 𝐏𝐵𝐞𝐬𝐞 qNMR method, the analyzed and internal standards were collected together. After that, we found that actually there is no need of collect the elute of internal standard as a step of purification. Therefore, we proposed the ISC 𝐏𝐵𝐞𝐬𝐞 qNMR method for further time saving and more controllable sample preparation. In this method, only the elute containing the analyzed need to be collected and dried before adding internal standards and deuterate solvent. And the sample and the internal standard for qNMR were not required to be accurately weighed before the qNMR analyst, and the result was corrected by the ratio of 𝐏𝐵𝐞 peaks between the test solution and the reference solution. So after we proposed this method, we try to further correct this method. So last year we proposed the post-collection purity correction factor for this method. Using 𝐏𝐵𝐞 analyze the target, analyze and its purity after purification. It can extend this method to samples where 𝐏𝐵𝐞 could not purify the original low purity samples to about 100% purity. So oxytetracycline was used as the target compound for this method, and the result was consistent with that of the direct qNMR after deconvolution. In part 2, we introduced 5 qNMR approaches integrate with HPLC separation. This method suitable for different range. Among these methods, the last one, post-collection ISC HPLC qNMR method, have the fewest elimination on the collection process. Our goal is to developing this method to remove the potential systematic error in qNMR and enhance the accuracy and its applicability. So there are 3 cases compared to other methods for peptide purity assessment listed in this table. Applying qNMR to assess peptide purity is more challenging because for peptide, NMR spectrum is always crowded due to the coest structure related interference. They always have similar amino acid residues to the main components. So I will give you 3 examples to discuss the feasibility of qNMR for peptides. The first example is the application of HD exchange in qNMR, which was posted by Dr. Huang in 2014. Proton exchange is general technique for NMR identification, but it's rarely used in qNMR. In this method, proton exchange was applied to remove unnecessary peaks of peptides and to make quantitative peaks isolated. And a signature peptide of an important proton HCG is used as the model compounds. We can see from the proton spectrum, there are 2 CH peak of tyrosine and not exchangeable proton, but they are subject to the interference from NH proton, which can see clearly in this picture. Okay. What we try is to add different amount of deuterium oxide into the sample, and by comparison, we found that 1% deuterium oxide is sufficient for accurate quantification. As we can see, the peaks of exchangeable protons decrease and almost disappear, and isolated exchangeable CH protons were then applied for quantification. So peptide T5 of HCG was also measured by hydrolysis IDMS. The CV of qNMR was smaller. The total experimental time of qNMR is about 1 hour with no need of any chemical reaction, much less than the hydrolysis IDMS, which may need 3 days. That is the second case, HPLC, qNMR HPLC, for measure the purity of human insulin. The process began with an original sample of HI, and the first step was to purify the original HI use HPLC to obtain a purified HI. The second step is to measure purified HI by qNMR and using CRM as internal standard. And the third step was to measure the purity of original HI by HPLC using the purified HI for external calibration. So this method, the result shows this method demonstrated greater accuracy than IDMs. For detail for the first step, purification. There is a common issue in proton purification that the sample are easily to degradation and poor in stability. So in this work, the stabilizer and the suitable HPLC parameters, also the freeze drying procedures were optimized. Finally, we obtained about 300 milligram purified HI with organic purity value over 99.7%. And the peak at 8.52 representing to one CH protein from hesitant was selected as the quantitative peaks due to the best resolution for other peaks. And malic acid serums were used as internal standard and mixed with purified human insulin, and dissolved solvent was deuterate dimethyl spiked with deuterium oxide, and the best resolution was achieved at 50 deuterium acid oxide. And what's more, about 1% of deuterate hydrochloric acid was proved to effectively reduce the exchangeable protein peaks besides the quantitative peaks. The organic purity of purified HI was accurately assessed by direct qNMR and be used as a standard to measure original HI. The purified HI was applied as an internal standard. According to to measure the purity of original HI by HPLC, according to the ratio between the concentration and the HPLC peak area of HI before and after purification, the purity of original HI was then calculated as 84.52%. So after that, the uncertainty of purity of HI sample was also calculated, which is 0.68%, which consider the relative uncertainty from LC measurement repeatability and from concentration of HI solution before and after purification, and from purity of purified HI sample measured by qNMR, also the organic impurity in purified HI sample. So this study tried to expand the application of qNMR to protons with a molecular weight of approximately 5,800. Yeah. Then the purity of human C peptide was also determined by the same strategy. Since there are no suitable non-exchangeable CH protein in HCP, the beta protein of aspartate acid residue was used as the quantitative peaks. In this case, let me see, 90.9 deuterium oxide was added to keep the resolution of beta protein of HCP aspartate acid residue. So this job, the result of this job is consistent with that of CCQM-K115, and the CV were produced by unknown peptide impurities, about 4.5% in the purified HCP sample. So the accuracy will improve if higher purity HCP sample can be obtained by better purification techniques or using the ISC or ISRC strategy that we have discussed in part 2. So to wrap up, qNMR has advantages including universal to almost all organic compounds, traceability to SI unit, and relatively simple pre-treatment. NIM have developed 6 internal standard CRMs to support protein qNMR, and the limitation of qNMR, such as low sensitivity and ability to separate foreign impurities, can be partly addressed by using high-field NMR with deconvolution and LC NMR coupled methods. So this method I just mentioned, including two-signal suppression, ST exchange qNMR, and the internal standard correction, and also post-collection purity correction, has been proposed to enhance the accuracy and convenience of HPLC NMR. So we think such technologies may facilitate the application of qNMR in quantification of low purity and also micro biomolecules. That's all for my presentation. Thank you very much.